All right, third video, concavity and points of inflection, featuring my cats whose favorite pastimes are looking out of windows. My other cat is also running around right now, but we got to talk about math. So we started off this section, 4.5.1. We started on this section by saying the derivative, the sign of the derivative, has to do with whether something is increasing or decreasing. Which direction is something going? Whereas here we're talking about concavity, which is really talking about how is this curving? Is it curving down or is it curving up? The first derivative has to do with direction. Second derivative has to do with the curve. Concavity has to do with which direction is things curving. We'll give a more formal definition here, and then we will also talk about this for, well, you can see the timestamp of this video. That's how long we're talking about it. I can't see it. It hasn't happened yet for me. So big, long, mega definition. If the derivative f prime is increasing over, let's add a bullet point here, over an interval I. So this definition starts off with almost the same definition as the first video. First video said if the function is increasing. This one says if the derivative is increasing. Well, remember what it means for something to be increasing. Something is increasing if the derivative is positive. So f prime is increasing if the derivative of f prime is positive. What's the derivative of f prime? Just add another prime. So this is just saying if the second derivative is positive, f prime is increasing if the derivative of f prime is positive using the stuff that we talked about in the first video. The derivative of the derivative is my friend. No, the derivative of the derivative is the second derivative. Okay? So if f prime is increasing over an interval I, then f is concave up. Sometimes you'll see this abbreviated CCU, and that's our first definition. We'll talk, you know what? Let's talk about it now. Let's not wait for the second and third parts of this definition. Let's talk about this now. What does this mean? Well, it goes all the way back to the first video that we did. I said, well, there's kind of two ways that something can be increasing. This first way and this second way. Now, look at the derivative. The derivative is the slope of the tangent line. In the first one, right, kind of a small slope here, and then the slope is getting bigger. So if it's curving this way, the slope keeps increasing. This is our concave up situation. And even if it's decreasing, that can happen as well. Let's look at that bottom right one. Here's another tangent line. The second one is less negative. It's closer to zero. Less negative is more positive. In here, this second one is the same situation. This one down here is also concave up. The slope is increasing. The slope of the tangent line is increasing. The derivative is increasing. And remember, increasing, if something's negative, means it's getting less negative. Think of the number line, right? If you're already positive, increasing just makes it a bigger number. But if you're negative, increasing is still traveling to the right. So -5 to -4 becomes, it's less negative, we say a lot of times. It's also increasing. Okay? That's how kind of this all connects. And that's when I said what I said when we talk about the curvature. What is this doing over here? And again, we have a very, very similar definition. If f prime is decreasing over an interval I, that means that f double prime is negative, what do you think we call it? If f prime is decreasing, we're not particularly creative. Concave down, often abbreviated CCD. All right, that's what we're doing over here. All right, and one of the ways that we kind of remember this, we do have a third part of this definition. Well, let's leave this third part blank for now. One of the ways to think about concavity is with parabolas. That's how I personally like to think about these. You can also think about them as like little smiley faces or something. But kind of like a memory trick, rule of thumb, I don't know how you want to phrase it. But like concave up, it kind of looks like this, like x squared. And concave down usually looks like this. This is not a mathematical definition, but it can be a good visual way to kind of picture it. The mathematical definition is look at the slopes of the tangent lines. Are the slopes of the tangent lines getting more positive / less negative? That means the derivative is increasing. The second derivative is positive, concave up. And similarly for concave down. But this is a good way that you can think about it, I think. We'll look at more of these in the future videos. We're pretty analytical, pretty mathematical now. Later videos have more connections. All right, so in this next one, next definition I want to mention is if f is continuous at A and f changes concavity, at A, then A comma f of A is a inflection point or point of inflection. I will often abbreviate it POI. The book often mentions inflection point. I'm missing a couple letters. All right, of the function f. And so if the second derivative is continuous, the only time that it can change from positive to negative, if the second derivative is continuous, is when the second derivative equals 0. Intermediate value theorem coming back again. All right, so those are our big definitions for this section. Concave up means the derivative is increasing, means it's kind of curving up. Concave down, derivative is decreasing, kind of curving down. And point of inflection if it switches concavity and if the original function is continuous. So let us use this a little bit. Let's do an example. Example 2. Find all intervals. We'll do it one analytical and one graphical. Find all intervals where f is concave up and all intervals where it's concave down. And list all points of inflections. P's of I, points of inflection. I'm just going to write POIs. Okay, and first one, going to be y equals x cubed minus 6x squared plus 9x plus 30. Looks similar to the last example, but it is a different cubic function. So to look at concavity, the definition of concavity has to do with the second derivative or the first derivative, but it's easier to use the second derivative, so we have to find the second derivative. Y prime is equal to 3x squared minus 12x plus 9 with the power rule. And the second derivative is just taking the derivative again, is 6x minus 12. So concavity just has to do with the sign of the second derivative. Where is this function? Where is this second derivative positive? Where is the second derivative negative? And for this last part, where does it change from positive to negative? So in order to answer that question, since this is continuous, we really only have to look at where it's 0. because the only way it can change from positive to negative, if it's continuous, is when it equals 0. Okay? So it equals 0 when 0 equals 6x minus 12, when 6x equals 12, when x equals 2. And we're going to do something that looks very familiar. Let's look at when x is equal to 2. Let's look at the sign now, not of f prime, but hold on, it's not really fitting. Let's look at the sign of the second derivative. And let's look at concavity. So for things that are continuous and things that are really nice, we're going to approach these the same way. Make a very similar little chart. Well, to the left of the function, to the left of 2, since this is continuous, when x equals 2, this is the only x coordinate where the second derivative is 0, which means since that second derivative is continuous, everything in this interval should have the same concavity, and everything in this interval should also have the same concavity. So just like before, we can plug in some number to the left of 2, any number to the left of 2, and see what is the sign of the second derivative. Well, if we plug in 0 here, we're going to get negative 12. So to the left of positive 2, the second derivative is negative, which means it's concave down here. You can write CCD for concave down, or you can write the frowny face. I'm not very good at making frowny faces. And similarly, we can pick some point in this interval because everything here is going to have the same concavity. So just pick something there. I don't know, we could pick 3 or 5, whatever. Something in that interval, you're going to get 18 minus 12 is 6. Doesn't matter what value it is. What matters is that it's positive. So everything to the right of x equals 2 is concave up. Why does my smile look so weird? Because a normal smile, it doesn't actually, normal smiles don't have this shape. Only weird, creepy smiles have this shape, I think, right? It's like a normal smile is kind of more flat, but like, I don't know. And that tells us the answer. So let's answer. It's concave down on this interval, negative infinity up to positive 2. 2 is not included. The second derivative at 2 is equal to 0, so it's not positive. It's concave up when the second derivative is positive on this interval from 2 to positive infinity. Again, we don't include 2. At 2, it is neither concave up nor concave down because the second derivative is 0. There's a point of inflection when x equals 2. What's the y coordinate? Again, it's a point of inflection. Points have x coordinates and y coordinates, at least in 2 dimensions. In higher dimensions, they have more coordinates. But we need the y coordinate as well. So when x is equal to 2, what's that y coordinate? That's going to be 8 minus 24 is negative 16 plus 18 is 2 plus 30, 32 maybe? We'll check with the calculator afterwards. This is where it's concave down. This is where it's concave up. And the point of inflection is at 2, 32. Let's visually inspect this and see if we're right and check our answer. X cubed minus 6x squared plus 9x plus 30. We are going to have to zoom a bit. All right. We said it's concave down to the left of positive 2. So to the left of positive 2, comma, what did I say? 32? Oh, good. That point is on the graph. To the left of that green point, it should be concave down. And in fact, if we look to the left of the green point, let's just look to the left of the green point. Does this look like an upwards parabola or a downwards parabola on this interval? Well, it doesn't really look like a parabola at all. But if I had to choose one, I'd choose it looks more like a downwards parabola, right? And we said it's concave up to the right of 2. And yeah, to the right of 2, look, it kind of looks like an upwards parabola. The slope is increasing. The slope is negative, but the slope is becoming positive. Slope is positive. Slope's getting bigger. The slope's getting bigger. The slope is increasing. That's what concave up means. And specifically, we said that there is a point of inflection at this green point. And yes, that's where it goes from concave down to concave up. And that's how it all connects. Let's do part B. Part B, I'm going to give you a graph. And we're going to take a little break from doing things analytically. I'm sure you'll be very sad about that. Or who knows, maybe you will be. I don't know. All right, let's look at a function, and let's say I'm not even going to try to make this look nice. We're just going to approximate. Our function kind of looks like this, like so. And there's not going to be nice numbers on this one. We're just going to try to visually inspect it to see. So our answer is going to be, where is it concave down? Where is it concave up? And where are our points of inflections? So let's visually inspect this graph. Try to divide it into pieces that we can say look like upwards parabolas, pieces that we can say look like kind of downwards parabolas, and etc. So this first piece, look at this first piece. Wow, that was terrible. Look at this first piece. This first piece looks like it's concave up. And then it looks like it turns into something that's concave down. And then it looks like something that is concave up. But it's not concave up for the rest of it. Look at this last little piece. The slope is decreasing in this last little piece. So in this last little piece, it actually is concave down again. And that's the trick one right there. So where does it change from happy to sad? Well, somewhere around here. Again, we're just estimating graphically. It doesn't have to be exact. Somewhere, I don't know, kind of around here. And the last one, somewhere kind of around here. Again, visually estimating here. So concave up here. There's not enough room. Hold on, let's see. I did this the other day. I made sure I made this work the other day. Hey, look at me learning technology. Okay. So it's concave up on that first piece. That's the piece from negative infinity up to, let's just say that's negative 1.5. And then in the next chunk, it's concave up. Sorry, concave down. Negative 1.5 up to about positive 2. The next chunk, concave up again from positive 2. So we're going to say union, positive 2 up to about 3, 4, 5, 6, 7. And then again after this, after x equals 7, it becomes concave down again. The points of inflections are the points where it changes, those blue points on the graph. They're going to be about, again, we're visually estimating, negative 1.5 comma 1.5, 2 comma negative 1, and 7 comma negative 2. And these are our answers. And we're really visually estimating in two different ways, right? I'm visually estimating where to draw the point, and I'm also visually estimating what the location of the point is in terms of numbers. And then again, just one more warning as we wrap up this video. One more warning about notation. Math, we reuse the notation all the time, right? F inverse of x that's not a negative exponent here. It's telling us about an inverse function, even though if it were like this, that's a negative exponent, even though they look the same. It's the same thing with points and intervals. So these two things look the same, look really similar, right? But the top one is an interval from negative infinity to negative 1.5. The bottom one is a point, negative 1.5, comma 1.5. So I don't like it probably any more than you do, but just be careful. So the intervals are connected by union signs, but the points are logically connected with commas. Because this is a single interval. This is a single disjoint interval, means it's an interval with pieces that don't connect. But it is a single interval, even though we write it as the union of two intervals. All right, so just quick little small conceptual things that are important, but can be tricky, not trippy. That's something else. Let me know if you have any questions, and good luck.